Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be talking about the origin of soil. Okay, now let me share my screen with you. Okay, let's start with the origin of soil. So basically, the soil is a conglomeration of discrete small solid particles, which is also called the soil solids. Some organic materials like rotten leaves or trees or dead animals, and some voids filled with air and water. Okay, and there is also a lot of microorganisms like bacteria in soil. Okay, so soil solids are usually formed by weathering rocks. So you can understand at the beginning of the earth, it was like a fireball. Then over the years that cooled a little bit and there was a thin crust at the surface of the earth, okay? But the temperature, pressure, everything was different at different location of the earth because of the climate. Some area had like desert, some area had sea, some area was close to the sun, some area was a little bit away from the sun. That's why a lot of temperature difference and other thing occurred, and that actually caused the weathering. Now, geotechnical properties of soil is primarily dictated by the minerals that constitute the soil particles and size and shape of the particles. We are talking about geotechnical properties, not other properties of soil, like which soil is better for which crop. That's not our concern here. We are just talking about the geotechnical properties. And we see that the property of the soil depends on which type of mineral that constitute that soil, okay? And size and shape of the particle. You can see the different size shape of the particle here. We'll talk about that a lot in the later part of this lecture. And now let's move forward. So based on the minerals that constitute the soil particles, we can divide the soil into two different classes. First of all is plastic soil and then non-plastic soil. So what is plastic soil? It's also called cohesive soil or fine-grained soil. Okay, this soil is very sticky actually when this one come to contact with water. Okay, so this type of soil contains primarily microscopic clay minerals, okay, and show plasticity and stickiness with the presence of water. On the other hand, the non-plastic soil, which is also called non-cohesive soil because they are not sticky, also called coarse-grained or granular soil, usually sand and silt. Okay, so this type of soil contains primarily sand and silt particles and show no plasticity or stickiness in presence of water. Just think about sand. If you take it in your hand, it's not sticky. All the particles are separated and granule. That's why it's called also granular soil. Okay. Now, plastic soil, it can be composed of clay minerals such as kaolinite, illite, montmorillonite, chlorite, halloysite, vermiculite, and attapulgite. Okay, but the most common clay minerals that we see is actually kaolinite, illite, and montmorillonite. The non-plastic soil, it can be composed of minerals such as quartz and orthoclase and gypsum, organic materials such as mollusk shells and coral fragments, and rock fragments such as basalt, pumice, or chert. But primarily, the component or minerals in non-plastic soil or sandy soil is actually quartz. Okay, but you can understand that you can see like sand in the desert or in the sea beach. You can see like clay soil in some part, purely clay soil I'm talking about, some part of our country. But basically most of the soil is kind of a mixture of clay minerals as well as um, quartz and other minerals too. Okay. Now, weathering of rock. Weathering is a process of breaking down of rocks into smaller pieces. So weathering could be divided into three categories, like mechanical weathering. Sometimes we also call that one physical weathering, chemical weathering, and biological weathering. Okay, you can see this is the weathering of rock. Okay, and this one is kind of getting smaller pieces and falling down here and making soil. Now let's talk a little bit about each of the type of weathering system. Like mechanical weathering or physical weathering is a process because of the temperature change, pressure change from the frozen ice, the running water, ocean wave, wind, etc. Okay, the chemical property doesn't change due to mechanical weathering. Okay, so you can see here, this is mechanical weathering. Okay, this one is kind of getting down from there, no chemical reaction at all. Now let's go to chemical weathering. Chemical weathering is a process caused by chemical reactions. So rock minerals are transformed into new materials or new minerals. Chemical reactions occur with natural carbonic acid, organic acid, or soluble salt, etc. The most common clay minerals which have plastic property is the product of chemical weathering of feldspar, micas, and ferromagnesiums. Okay, so you can see a lot of chemical, like weathering system here. Now, biological weathering. So it's a form of weathering caused by the activities of the living organisms. For example, the growth of root or the burrowing of animals. Okay, so you can see some of the, like it's a fox making a big hole here and trying to make the particles, like smaller pieces. Similarly, you can see that this is kind of like a kind of algae in the water that's trying to decay this stone here. You can also see here that, let's say this was a big rock here and then a small tree started here, then tried to put the root inside the rock, created huge pressure and trying to dismantle the rock. Okay, so this is a example of biological weathering. Now, transportation of weathering product and how soil is being moved from one place to another place. Okay, so residual soil that remains at place of origin, but most of the soil is not residual. They will just move there for different reasons. So transported soil that are transported to other places. Transported soil can be classified based on the mode of transportation. Okay, we are talking about 6 different type of transported soil, but it could be more than that. Okay, now let's say glacial soils. These are moved by the glaciers. Okay, I'll show a picture in the next page. Alluvial soil, that's transported by running water. Water will just dissolve, not dissolve, suspend all the soil particle into it, move when this one is flooding, and put all over the places, and the water recedes slowly, so they will be deposited on the plain. That's called the alluvial soil. Lacustrine soil that's basically formed by the deposition of a quiet lake. Water is coming from every side to the lake, and they have a lot of soil particle there. And when the lake is very quiet, then basically all the suspended particle will be sedimented. That's actually lacustrine soil. Marine soil, which is formed by deposition in the sea. Okay. Aeolian soil that transported by deposit by wind. Sometimes you can see dust storm or like sandstorm, and they will just move soil from one place to another place. Colluvial soil transported by gravity during landslide. Okay, so let's see some of the picture of that different type of transported soil. So here you can see the alluvial soil. Okay, that's coming when the river is flooding. Then basically you can see the lot of sediment in this water compared to here, right? So when it flooded, then basically soil layer will just, water will come here, 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 and also there. And when the flood water releases very slowly, then basically some of the soil particle will deposit on the top of the bank. And that's a very small, deposition, maybe like a couple of millimeters or, something like that. But over the years, you will see there is a thick layer of soil that will be deposited there. That's alluvial soil. This is colluvial soil. You can see the fragmentation of the rock at the top here because of the root and everything. And then because of the gravity, they're falling here. So these are basically colluvial soil. This is glacial soil because all the glaciers here, which are also mixed with like different type of rocks and soils. And when they come from here to here, they will just bring all those soil with them. Okay, and when the water drains out, then basically you will see some soil particles there. That's called the glacial soil. So aeolian soil, you can see this is a dust storm, and taking a lot of dust in the air and trying to move like here and then basically settle down there. Okay, this is marine soil, similar type of things, like sometimes they will just take the soil out from the bank and move to the other, like another site there. Okay, so that's basically marine soil. And this is your lacustrine soil deposits, actually taking the closer picture there. You can see these are basically very fine material because of the nature of the quiet lake. The lake is very quiet, so actually all the suspended particle in the lake that came with the water that entered the lake, and now they are slowly depositing there because of the uh, gravity actually. So that's making a very small thin layer every year. And if you see like after 100 years, 200 years or 500 years, you'll see a big thickness of that kind of soil. Okay. Now we have to talk a little bit about clay minerals. I'm not gonna go that much details of that thing, but we definitely cover like which is very essential for a geotechnical engineer. Okay, so clay minerals, I'm talking about clay minerals, not the minerals that constitute sand and silt, not about quartz. We are talking about clay minerals, okay, because this is kind of important for us. So clay minerals are complex silicate composed of two basic units, silica tetrahedron and alumina octahedron. This is silica tetrahedron. Tetra means four. They have like four faces here. These from the other side and the bottom base here. Okay, so four sides. Three sides here and the bottom. Okay, and this is here that middle. You can see there is a silicon, and this one is oxygen, 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 and oxygen. Okay. And this one is alumina octahedron. So this is your aluminum. And basically this is hydroxyl ion, 1, 2, 3, 4, 5, 6. And you can see this one has 1, 2, 3, 4, 5, and then bottom 6, 7, 8, total actually 8 faces. Okay, so that's why it's called octahedron. Now, basically, the most common 3 clay minerals, which is kaolinite, illite, and montmorillonite, they are nothing but kind of like this combination of silica and gypsite sheet. Gypsite sheet is the aluminum, this one here. This alumina octahedron, this is also called gypsite, okay? Gypsite sheet. So basically, all that 3 type of clay minerals is a combination of these 2, and then basically there might be other minerals or element there too. Okay. Now, clay minerals have negative surface charge, so they try to attract positive, like surface charge. Okay. So why the clay minerals has negative surface charge? Because of the 3 reasons. First of all, the silica sheet. If you see silica sheet here, then basically this one has 4 oxygen, which has 8 negative charge, right? And then you have aluminum, silicon at the middle, which has 4 positive charge. But what happens, like the 3 bottom, like oxygen, that actually, goes with the other one here, okay? And this one here. So all that 3 in the bottom is actually a continuation of the sheet. So basically this one will be used up with the other side. This one would be used up in the other side, and this one will be used up in the other side. But this one here, that negative charge, 1 negative charge here, is always extra there. So that's why this one creates some negative charge of the clay minerals. Now you can see the second thing is called the isomorphous substitution, which is nothing but if you change that, let's say, silicon with aluminum or any other metals, then basically without changing the lattice here. So let's say, for example, if I change that one with aluminum, then what will happen that there would be like 3 positive here. So I'll have not 1. Now I'll have 2 more negative charge extra there. Okay, that's what we call isomorphous substitution. Means the substitution of silicon by other metals without changing the lattice of the like structure. Okay, so the third one is break of continuity at the edge. So you can see here that if you break it here, then basically there is 1 negative charge here that will create like doesn't have any, like continuation. Okay, so that will create another extra charge there. So that's why we see that clay minerals as smaller are they, basically they have more negative surface charge. Now you can see the clay minerals and they have their surface charge here. So kaolinite has the lowest. Mica or chlorite, they have like in the middle. And montmorillonite, which has the highest actually. Okay, so if the soil has montmorillonite clay particle, a significant amount there, then basically the soil would be very, very sticky, like our San Antonio clay. Most of you saw that the San Antonio clay is usually black color, and they have a lot of montmorillonite clay, almost like 30–40% montmorillonite clay minerals, and they have highly surface charged So they try to attract water, and they feel very, very sticky uh, when they mix with water. Okay. So diffuse double layer. What this one is trying to say, that let's say this is a clay particle, okay, and they have negative surface charge here, negative surface charge. Now, if you take that clay to kind of a water surface, like close to water, then what will happen? The water might have itself some positive ion like calcium, magnesium, sodium, very common, right? And what will happen, like you will see that they will try to, in the solution here, they will try to, what will do, the positive charge will try to come here, okay, to neutralize the negative charge here. Now, what happens, like when you see that in a solution, when most of the positive charge is trying to move this way, that will create a difference in concentration of positive charge and negative charge. So that's why this one will try to diffuse from here to here, okay? So that's why you will see there will be a balance between these two, okay? So we call that one diffuse double layer. First layer is just the positive ions here, and the second layer is the mixture of positive and negative ions. So if you think about that anions, and these are the cations. So at a certain distance, you can see the concentration of ions at a certain period. They will have like the at this, let's say, distance, at a certain distance, you will see that there are a lot of cations here, and here they will just make that balance here. The cation and anions are now kind of like the same level, and they can just neutralize each other. Okay. Now what happens, like if there is no metal salt present in the water? Okay. So in that situation, what happens, like you can see, this is actually water there, and water can easily polarized in such a way that one side is actually hydroxyl ion, the other side is hydrogen positive ion. Okay, so let's see that one here. In that situation, what will happen, that the water molecule will try to, polarized in such a way that the positive charge of the hydrogen will be close to the clay minerals, and the oxygen, like the anions, will be in the other side. Okay, and that's why what they will try to attract that water molecule very close to the clay minerals. Okay, now you just think about all the minerals are kind of conglomerated there. So basically they will try to share that positive charge of the water with the, like the electro neutral, to achieve the electrical neutrality, they will try to adhere together. Okay, so that's why they have a high affinity, like clay minerals have very high affinity with water. They try to hold the water, doesn't allow it to dry easily, because they try to hold that one to, uh, quench their thirst for, like positive ions. Okay, so that's why they absorb a lot of waters. So you can see here that this is a typical, like one, excuse me. So you can see this is a monometalonite clay particle here, and this one is actually the water that will be absorbed to neutralize the negative charge of the water. You can see it can almost, absorbs 9 times of its own volume. Okay, so there are a lot of water they can hold. On the other hand, this one is actually kaolinite particle. Their charge, surface charge is much lower than monomerilionite clay. So they can just, absorb some. This is the particle itself, and they can absorb some water here. Okay. Now, this is some of the specific gravity of the common clay minerals. You can see usually the quartz is like 2.65, kaolinite is 2.6, illite is 2.8, monomerilionite is 2.65 to 2.8. That's why we usually see for quartz or pure sand, the specific gravity is always 2.65 plus minus zero point 0.5, plus minus 0.05. And for clay, the specific gravity of the soil solid is a little bit higher, many cases. If you have more illite there, if you have more kaolinite, then basically you will see a little bit less than 2.65. Okay, I'm just talking about the specific gravity of the clay mineral, clay solid, not the bulk soil. Okay. So this is the summary. The soil solids are usually formed by weathering of rocks. Geotechnical properties of soil are primarily dictated by the minerals that constitute the soil particles and the size and shape of the particles. We'll talk about the size and shape in another video. Based on the soil minerals, soil can be divided into two classes, plastic soil and non-plastic soil. So non-plastic soil, which is basically sand and silt, is composed of primarily quartz and rock fragments. Okay, they don't have any clay minerals there. On the other hand, the plastic soil, which is clay or muddy soil, is composed of primarily clay minerals, such as kaolinite, illite, and monomerilionite. So clay minerals have negative charge, surface charge, and they have great affinity to water. And the physical properties of non-plastic soil remain unchanged with the presence of water, whereas plastic soil changes its property with the change of water content. So if you add water or take water out from the soil, actually sand doesn't have any change in its strength property. On the other hand, for clay soil, if you add water or take water out from there, their strength property changes. Okay, so that's why clay soil is a little bit more, kind of troublesome for geotechnical engineers. And we'll definitely discuss about that in later part of this course, but I'll just stop it here for the origin of soil. So if you have any question, please feel free to contact me and come to the office hours, and then we can just discuss that one in our Zoom session. Okay. Thank you so much for watching.